Okay, thank you. What a pleasure to be here. I'm incredibly excited to join TERC, to join UC Davis, and this is week 7, and it's just been phenomenal. I've really enjoyed getting to know the team and getting to know the community members, and it's hard for me to believe that at only week 7, I look out in this audience and see so many faces that I've already met. So thank you for welcoming me into the community. So at week 7, it's still too early. I'm sure you can all recognize for me to tell you everything that's about to happen on Tahoe. And indeed, if you have questions about Tahoe, I'm not shy about turning to the experts in this room and saying, I don't know, let's ask this person. So, but happy to talk about Tahoe because I'm thrilled to have the opportunity to work here. What I will talk about is about some of the research that I've been doing over the past several decades. And I'll give you a little bit of context to tell you what motivates me in the type of research that I've pursued. And then I'll talk about just 2 of the research areas that have been dominant in my research profile. And I have a member of my lab here tonight. And so I know he's sitting there saying 2 areas of research. She has like 12. So they're very patient with me. So the context here. So maybe it's my background, beginning my research career in the snowpack-driven mountains in Nevada, but I see my job as a freshwater biologist as to figure out how the large-scale climate dynamics drive the ecological change that we see occurring in freshwater. And these changes in freshwater are largely caused by microscopic life. So I move among microscopes and water chemistry to climate models from regional to global scales, crossing these scales. And when we look at the globe, we're really struck by this blue planet that gives us a sense of the abundance of water. But most of that water is in the oceans. We can't use it for most of our needs. And to illustrate this, I'm going back to the way I was taught about the real natural scarcity of fresh water on our planet. I was taught it this way when I was an undergraduate, and I still find it one of the most visually effective ways to talk about the scarcity of fresh water. So 97.5% of the surface water on our planet is in the oceans. And so you visualize that as a familiar 2-gallon milk jug like this one, and that represents the oceans. That's all salty water that's hard to use. So if you put 3 ice cubes in there, that represents the fresh water on surface that is in glaciers and ice caps. And so not only is that hard to use, but those are really important in the climate cycle. So we really shouldn't be harvesting fresh water from those ice cubes. And that's 2.4% of the surface water. Now, if you pull some of those ice cubes out and you let the drops drip off of those ice cubes, 16 drops. That's what represents the renewable liquid fresh water that's found on the surface of our planet. 16 drops against this ocean of water on Earth. And so that's 0.02%. So that's less than 1% of the surface water that is fresh water on Earth. And I know that that's hard to get our heads around when we're sitting next to this big, beautiful lake. But that is the real value of our water. So surface water, unlike groundwater or the water in the oceans, it's accessible. It's renewable by rainfall. It's fresh. It's very ready for human use. So this picture is the Ashokan Reservoir. And it's one of the reservoirs which is in the system of protected watersheds that provides 90% of New York City's drinking water. So it's up in the Catskill Mountains. So how does the Ashokan Reservoir stay full when New York City keeps drinking it? It's large-scale physical processes that are moving water around our planet, like the lake effect snow that moves water from Lake Erie and Lake Ontario to the Catskill Mountains. where New York City's water supply is located, and it's circled here in red. So lake effect snow, yes, I'll answer you in advance. It does sometimes happen at Lake Tahoe. Lake effect snow occurs only on very big lakes under certain circumstances when wind that is much colder than the water moves across the lake and picks up that water as humidity. The wind warms along the way, rises, snow forms, and drops on the other shore, which is totally terrifying if you live in Buffalo, right? This is the wall of lake effect snow coming into Buffalo. But it's fantastic for water supply because that fills up the snow in the mountains, in the Catskill Mountains. And as everybody in this snow-driven system knows, that's the water, that's tomorrow's water, really. And so lake effect snow, just lake effect snow, contributes about 1/3 of the total water renewal in the Catskills watershed. So it's super important to New York City's water supply. And I will tell you that when I've given some version of this talk on the East Coast, I truly believed that New York City's water was the best water I'd ever tasted. It really, I mean, the Catskills reservoir system is an engineering feat. And the water in New York is really, really good coming out of the tap. But now I live in Kings Beach. I gotta say, the water here is really, really good. So I'm very, very pleased with the water quality here. So in speaking about big physical processes moving water around, in the West, we're becoming experts on another large-scale process that generates big water events, atmospheric rivers that can move twice the capacity of the Amazon River from the tropics across thousands of kilometers to make landfall in the West. And we've all heard of atmospheric rivers here by now. So they replenish our reservoirs. So that's great. But as you know, most of the West, a lot of the West really wasn't built for what we have been experiencing from atmospheric rivers in recent winters. And this picture is from San Jose in one of the recent catastrophic flooding events associated with atmospheric rivers. But even a wet year like we've had last year hasn't been enough to counteract the long-term drought that the West has seen for several decades, right? Combining decades-long drought with unsustainable water use, Lake Mead, which supplies my mom's water in Las Vegas, has been at about 35 to 38% of its total capacity in recent years. So I'm not saying it's down 38%. I'm saying it's at 38% of what it could be at 100% capacity. So it's a real conundrum to solve. And the thing I like to step back and think about is that these stories of abundance and loss of water at very, very large scales, these are all about these precious 16 drops of water next to an abundance of seawater and those 3 ice cubes that represent the glaciers and the ice caps. This is a tiny fraction of life on Earth on which everything depends, and that it's really our responsibility to steward. 70% of fresh water used in the US comes from this tiny fraction of Earth's water supply for our drinking water, agriculture, industry, and more. And I'm sure you know that California state recognizes that water used by 75% of Californians comes through the Sierra Cascade watersheds as surface water. Everywhere water touches down, it sustains life. And it's not just the fish and the wildlife that are so visible to us, like this gorgeous dipper that has pulled a caddisfly larva out of its case. But it's also the microscopic life that colors this water green. And sometimes, you know, even though it's microscopic, sometimes you can see little specks dancing around in the water. And those are my little friends that I know the most about. So all water is teeming with microscopic life. It forms the base of the food web. Everything that lives in water needs this microscopic life. So the phytoplankton, or the algae that are taking in the energy of the sun and turning it into food that the zooplankton can eat, these microscopic little animals that eat the algae, and the microbes that break down the things that die, the bacteria and the fungus. So together, this microscopic world controls water quality. So these microscopic organisms grow rapidly. They can have multiple generations in a single day, or in a single week. They can double in hours, days, and weeks. So they can change very, very fast. And without microorganisms, fish would have no food and water would become unusable. Microscopic life really supports healthy ecosystems, but as I'm sure you know, sometimes microscopic life can get out of whack and cause nuisance conditions like this algal bloom on Upper Klamath Lake. So those conditions are unpleasant and sometimes they're toxic. So it's totally fascinating to me that water availability is driven by these large-scale processes like the lake effect snow or the atmospheric rivers that come and pummel us with rain and snow here on the West Coast. But it is something this tiny that determines our water quality, this active, teeming life that can rapidly grow, double in days, hours, weeks, that it's something so tiny that it is controlling our water quality. And so this is how I end up switching back and forth between this large scale and this small scale. So hopefully that context helps you to understand my motivation. And now I'll tell you about just 2 areas of my research. And it's funny, I just realized the clock on my presentation has been running for 199 minutes. Oh my God, I hope I haven't been talking that long. All right, so I'm gonna look at the real clock. All right, so I'll tell you about 2 areas of my research. So in freshwater ecosystems, an important time of resetting the ecosystem has been winter. So the growth slows down with cooler temperatures, slowing down the growth of algae and bacteria and helping to keep them from getting really out of control. And so, you know, you take your leftovers and you put them in the refrigerator so that you can slow down the growth of bacteria and fungus. And it's the same under ice in lakes, is that things really slow down and it keeps it from going out of control. So unfortunately, winter has also been a time of year that we understand the least about, primarily because it's really dangerous to work on lake ice in the winter. My group has been leading international efforts to increase our understanding of life under the ice so that we can better understand some of the processes that are changing as ice changes around the world. So by pulling together data from satellites and also data collected by hand or sensors in the water, including the Lake Tahoe buoy, we demonstrated that lakes are warming rapidly worldwide with climate change. And actually, this was quite an interesting study because there were just a few that seemed like they were staying the same or cooling. And there were so few of them that we could go and look at each one and research it and see why are these cooling? And each of them had a fascinating story, like the lakes on the Tibetan Plateau that are getting cooler because glaciers are melting into them. So, but overall, it's fair to say that lakes are warming worldwide, and where they're not, there's some really interesting story about why not. One of the most profound effects of the warming has been the loss of ice on lakes and rivers. So ice cover begins later in the year and it melts earlier in the year. And you may have heard that some of the recent winters, especially if you have connections in the Midwest or in Canada, some of the recent winters have had record low levels of ice. And this has been surprising people who are used to using the ice during the winter, frequently for recreation, but sometimes for really important needs like travel across the lakes. And so they've been surprised by bad ice during the winter. And there were a number of rescues. There were a number of not only rescues, but also fatalities associated with people just being totally blindsided by the ice conditions not being safe for them. So it's increasingly clear that the loss of ice is taking a toll on people's livelihoods and in some cases lives, unfortunately, especially for those that are accustomed to using the ice for recreation or for transportation. What's less clear to us is what these changes in the ice mean for water quality, for habitat, for fish and wildlife, also greenhouse gas production. Sorry, I should have told you what you're looking at. These are, we're looking up at the ice from a camera that's in the lake, and these are methane bubbles that have accumulated under the ice and have actually gotten captured in the ice in some cases. So we don't know that much about what all these ecological processes, how they're going to change as these ice conditions change. And so we have tried to summarize what some of these changes may be in a recent paper in Science last year. And so I have a lot of QR codes, so please don't be shy about, I'll just be flattered if you want to look at my papers. So don't be shy about getting your camera up there. But I'll show that one again. Okay, so we don't know that much about winter in most lakes that have ice cover, but certainly there are some systems, some ecosystems where there's a relatively large amount of research that's been done on winter ecology, like Lake Baikal in Siberia, where I've worked with an international group of researchers for about 20 years. So Baikal, I know people around Tahoe know more about Baikal than most audiences, but I like to talk about it, so I'll tell you a little bit about it. So it's huge. It's visible from space. It covers about 4 degrees of latitude, so that's about 650 kilometers long, similar to the footprint of Florida, if you want to try to picture it that way. It's very remote. So it's 5 time zones away from Moscow. It's 4 time zones away from Vladivostok, which is at the eastern edge of Russia. So it's really a very remote place. So you may have heard that it's frequently called a lake of superlatives, meaning it's just the most of everything. Everything you can think of, it's the most of. And that's almost all true. So it's the highest volume. So it holds 20% of the world's fresh water. You could take all of the North American Great Lakes combined and pour them into Lake Baikal. It's the deepest lake. It's about 1 mile deep, and it's a rift lake, and so it's deep sort of through most of the basin, which is how it holds all that water. It has the highest biodiversity for a lake. It has the highest level of endemism, meaning that more than 50% of the plants and animals aren't found anywhere else in the world. And all that biodiversity may have been it's partly because it's the oldest lake that we know of. It's 25 million years old, at least. And so it's been around a long time, a lot of opportunity for organisms to adapt to those conditions. Okay, so why do we know so much about Lake Baikal? It's a really remote lake in Siberia, but this is an unusual case where 3 generations of a Siberian family have been doing research on this lake. They have taken samples every 2 weeks through all seasons of the year, beginning in 1945. Yeah, with Mikhail Khrushchev. And when I say through all seasons of the year, I've seen a lot of long-term data sets. They all have gaps in some places for totally normal reasons. And when I saw this data set, it has the fewest gaps I have ever seen in this 60-year record. So Mikhail Koshov was a professor at a Siberian university, and his daughter, Olga Koshova, also became a professor and continued his research program. And then his granddaughter, Lyubov Izmesheva, this little girl sitting here next to her grandfather, she also became a professor and a researcher and continued this research program to produce this amazing 60-year data set on Lake Baikal. Okay, so it's fair to say that no one in the world, no one in the West, I'll say, although many Russians also don't know about this data set. So I would say no one in the West would be likely to know about this amazing data set, except that my colleague Marianne Moore from Wellesley College has been taking her students to Lake Baikal every 2 years for quite a long time. And so she took her students there one year, and Lyubov was giving a talk through translator and referred to the 60-year data set, and Marianne just thought it was a translation error, and so she just blew it off and forgot about it. And then 2 years later, somebody else mentioned the 60-year data set, and she was like, oh, excuse me? And so she came back, and luckily for me, she remembered that I have expertise in working on large data sets from lakes, and she called me when she got back. And this was a story, a really beautiful story that the New York Times published about that work. So my role on that project is using multivariate time series statistics to relate plankton food web effects to climate change. It's similar to what I did for Lake Washington in Seattle, which is a lake where a long-term monitoring program helped to document the positive effects of diverting sewage from Lake Washington. And Lake Baikal's data set actually structured pretty similarly to that data set. And so I did a lot of analysis on that for many years. And of course, these are things that I'd love to be able to apply to the long-term data, this amazing, rich resource that we have here at Lake Tahoe. Okay, so Lake Baikal gives science a lot of interesting phenomena to consider. And you know, maybe later this year, I'll give a talk that's just about Baikal. One of the most motivational for me and my team has been the importance of ice. The long-term data that are collected by our Siberian colleagues really strongly demonstrate the importance of ice. The highest concentration, the highest mass of algae occur under the ice in Baikal. So there we go. So we've got month here on the x-axis, and this is chlorophyll, which is a pigment proxy for how much algae is in the lake. And it's pretty evident that you get this big peak of algae under the ice, which many people for many years thought was a really weird thing about Baikal. And here, still looking at Baikal, we're looking at a photo where my colleague has put a GoPro on a pole that he put under the ice, and now we're looking up at the ice, and you can see this mat of algae that is attached to the ice or just right under the ice. And these blooms, we did a lot of work. My colleague, my husband, Steve Katz is here as well, and he worked with me on some of the research showing that these blooms primarily occur when the ice is really clear and when the wind has swept free the snow, so that you get a lot of the sunlight coming through this clear ice and fueling the photosynthesis that can occur under ice. So a lot of those cold water algae also are especially nutritious for the zooplankton that eat them. And so they may give the zooplankton a little extra boost of nutrition during the winter, a boost that is nutritionally maybe better than summer. So when you think about going through the grocery store and looking for foods that are high in some of those healthy fats like omega-3 and omega-6, those are the same kind of fats that are in these algae. And indeed, when you're thinking about some of the fish that may be high in those healthy fats, many of them have eaten foods that are coming from cold water, where the algae tend to accumulate these types of fats. So we're still under the ice here in Siberia, and I find this photo terrifying. So Siberian divers are very brave. And this is not me. There are a lot of things in this photo I would not do. But this is a Siberian diver under the ice. And you can see some of the breakup of the ice starting to occur. And our Siberian colleagues have suggested that when the ice melts, when it starts to break up, the algae actually falls off of the ice in these kind of tufts, and then it floats around on the bottom of the lake. And the organisms that all live on the bottom of the lake, then they all get to eat all of these healthy algae that just fell off. And so that's the kind of thing that happens in marine systems. This is still Baikal, even though it looks like a marine system. It's the kind of thing that happens in polar marine systems, but we just don't know if that's also what is happening in Baikal. But there's a really good suggestion that the critters that live on the bottom of Baikal, yes, indeed, in these sponge forests, which also are weird and very cool in Baikal, that those organisms probably get a lot of nutrition from that algae that falls off. Okay, so the bottom of the food web is dependent on ice in Baikal, the algae that capture the sun's energy right under the ice and turn it into food for everyone else in the lake. But the top of the food web is also dependent on the ice. So the top predator in the lake is the Baikal seal. And if you're wondering, is that weird? It is weird. So the Baikal seal is the world's only exclusively freshwater pinniped. So it gives birth to its pups on the ice. It also molts on the ice. And so it really depends on the ice. So this is a food web that really has adapted around being frozen for 6 months of the year. And obviously I could say a lot more about Baikal after 20 years, and I promise I love to give Baikal talks if you guys want to hear one at some other time. Okay. But as Braden knows, I do a lot of other things. I have many other projects. So while we at Baikal were thinking about the importance of ice, it became clear at international conferences, just talking to people in hallways, that there are a lot of people who think that something important is happening under the ice in their lakes as well. And so many of them had little bits and pieces of data that they hadn't published yet, or they didn't know what to do with. And so I sent out some emails on email listservs just saying, hey, do you guys want to get together and put our data together and see if we can understand what is happening under the ice in lots and lots of lakes, not just one by one. And the response was really overwhelming. Ultimately, we have 100 lakes represented where we've pulled together the data to understand what lives under the ice and how might it be changing as the ice changes. So what we found was that lakes are actually really, really active under the ice. There is a lot of algae, there's a lot of zooplankton. In most lakes, there's a lower activity, right? We're kind of in the refrigerator under the ice. But on average, winter, for example, had 40% of the algae that you would find in that lake in the summer, which is less, yeah, but it's still a lot. And there were many lakes other than Baikal that also had their greatest production of algae during the winter. So it's a pretty exciting time, and it's likely that, well, it seems extremely evident that changes in the winter, activity in the winter, do have repercussions year-round. So beyond working in these single ecosystems like Lake Baikal, I spend substantial amount of my research time organizing international research efforts to get a more global understanding of freshwater issues. So right now, we all see this urgent need to increase our understanding of ice-covered winter ecology before ice becomes way too unpredictable for us to do that research. And so we have a grant from the National Science Foundation to mobilize that effort. And it includes work on mountain lakes in the Sierras, led by our UC Davis colleagues, Steve Sadro and Adrian Smits. And I know that right now, Sudeep Chandra has some of his crew out on ice-covered lake out at Castle Lake today, collecting data for that project as well, because this is a big network that we are expanding. So we're scaling way up in this new project, launching this 4-year campaign. We're in the first year to compare winter and summer sampling across 60 lakes in North America, hopefully from some other parts of the world as we build up our network. And we'll get a better understanding of how lake ice dynamics are changing, how they affect the plankton that drive water quality and that provide food for fish. And as part of this project, I think one of the most important things that we've done is to teach other people how to do research on ice, because it is dangerous and it's also extremely challenging. You need to protect your safety, you need to protect your colleagues' safety. You also need to know that your equipment is going to freeze, and you need to know what to do when that happens. You need to know that your batteries will die sooner than you expect. And you need to know a lot of tips and tricks about working on lakes and some of the special tools that you will need if you're going to work on lakes and that are covered with ice. And of course, everyone who works on an ice-covered lake has to have a picture of themselves with an ice saw, because it's really extremely cool. And we had some first responders who do trainings who came out to do a training on how to rescue yourself, which is awesome. And then also how to rescue others. And the rule of thumb is don't go on the ice unless you're prepared to go through the ice. And so it's a simple thing to keep in mind as you look down at yourself before you walk on that lake and say, how's this going to be in the water? Is that okay? Do I have some ice picks that could get me out of this situation? Right. So it was great training. We're really hoping to be able to do that again soon. And this training that we did last year, we were doing it at a time when the ice was just a mess in places where it really matters, in the upper Midwest and in Canada. So this is an ice road across rivers and lakes. It's part of a network of ice roads that connects very remote communities that rely on those roads for connectivity. And the ice roads at the time that we were running that winter school, they had been closed for most of the winter, and rural communities ran out of food and fuel. And so several First Nations declared states of emergency so that they could get food and fuel to these communities. So overall, freshwater ice is more important to societies globally than may be evident for many of us living in California and Nevada or in the West. But most of the world's lakes freeze. And on average, they are covered by ice for about half of the year. We made this map that shows the world population around lakes that freeze. So this is about more than 1 billion people who live near a lake that freezes. They use them for drinking water, for fisheries, transportation, and a lot more. And the rate of lake ice loss has dramatically accelerated over the past 25 years, with ice melt arriving on average 45 days earlier per century. And so this is a lot of people. People are definitely noticing these changes, and it matters to them. And right now we're losing that ice without a really clear understanding of what we are losing, which lakes are going to be good refuges for fish and wildlife as the ice conditions change. So our results may help us to anticipate some of those new states of ecosystems and prioritize conservation or restoration actions. We're still really, really early in that frontier. Which lakes will experience more summer algal blooms when the lakes have less ice, or greater immobilization of the pollutants from the lake sediments, or emissions of greenhouse gases. So the effects of warming don't stop in the water column. We know that warm temperatures and lower oxygen cause biogeochemical reactions in the sediments of the lake that release pollutants from the lake bed. So warm water, as a basic principle, can hold less oxygen, and that causes these biogeochemical reactions that can release some of these nutrients and pollutants, including nutrients released from the sediments that then work together with these higher temperatures to increase the growth of algae, both in the water column and in the sediment water interface there at the lake bed, where many of us are seeing increased nearshore algal blooms, which may or may not relate to nutrient additions. So this is something that I've been working on for quite a while. So this is the second area of research that I'll tell you about. So I've been working on the food web and water quality effects of these nearshore attached algal blooms for I think about 20 years. So I started with working in Olympic National Park in Washington State, where the park scientists and managers needed to understand what some of the food web effects of these nearshore algal blooms might be. So they have some endemic trout in these lakes, and they were noticing that the trout were avoiding some of the areas of the densest growth when they build their redds. And the park scientists marked these redds. Redds are sort of trout nest. They marked them with pink rocks, so that's what you're seeing there. And they were seeing that the trout were avoiding the densest areas, and that meant some of their redds were starting to overlap. And so the park scientists are very concerned about that and asked us to see if we could figure out why these blooms were happening and also what the food web effects might be. You know, maybe they provide good food for things trout eat. Let's find out. So that was what we worked on in Olympic National Park. And incidentally, when we were doing that work, we used some of the methods that were developed by my undergraduate advisor, Stan Loeb, while he was a grad student working here with Charles Goldman on Lake Tahoe. So this picture is Stan diving in Lake Tahoe doing some of the work on periphyton, and it appeared in National Geographic. So I had seen that photo when I was an undergraduate, so I kind of knew what Stan did, but you know how you never really know what your professors did? So then I was later working in Olympic National Park and started working with Stan's methods in Lake Crescent in the park. And then we did similar studies at Lake Baikal, where nearshore blooms are also becoming more common. And most recently, I've been thinking a lot about how to develop an inexpensive and accessible protocol that allows us to study the sediment water interface dynamics that may be contributing to these blooms. And I had the chance to test out some of these methods at Sudeep's invitation to go up to Castle Lake with his team and some of our colleagues last year. So we're still trying to figure this out, but it's high on my priority list of issues that I want to tackle. So that's it for my research, and hopefully I didn't give you whiplash moving between the large scale and the small scale, but if I did, then welcome to my world. So I go where the science tells me, and I believe that this is what it takes to provide understanding and stewardship for these precious drops of water that support life everywhere. that we find it on our landscape. And I am just thrilled to be here. And I look forward to the many years ahead interacting and working with you all. Thank you. Questions? So you don't feel that UV light affects algae? Oh, UV, yeah, UV can have some photo inhibition effects in the surface water. Yep. But it definitely affects the aquatic weeds. Mm. Have had low solar flares. Got it. I actually, and I'm going to summarize the question for Zoom folks. So the question is about how solar flares, solar flare activity and resultant patterns in UV would affect algae and the aquatic plants as well. And I confess I don't know very much about that issue. I do know that we monitor UV in Lake Tahoe. We have a good long record of that. And so we have some great resources for looking at UV dynamics. Thank you. Questions? Yeah, in the back. Yeah, are there certain species of algae that are more are better suited to the winter than the summer? Yeah, you definitely do see some winter, more characteristic winter algae, and you know, and they tend to be the ones that have this higher content of the polyunsaturated fatty acids that I was talking about, these omega-3s, omega-6, and a whole suite of other fatty acids that help with the mobility of the cell membrane under cold conditions. And so I mean, there's definitely some overlap of the summer and winter algae, and you can, you know, I can get surprised by a big, you know, bloom of, you know, something that I usually think of as a summer alga. But yeah, you do see them change a bit from winter to summer. Yep. Yep. Lake Tahoe doesn't stall. Yep. I do know that. I do know. It's okay. I've got 11 other areas of research that I can deploy here. Yeah. Yeah. Whoa, yes, Lake Baikal freezes, yes. The question is like, Lake Baikal is huge. Does it freeze that much? Yes. So we're talking a couple of meters of ice. So we'd be like 6 meters or 6 feet of ice, clear ice, and across the whole lake. Oh yeah, no, and the, you know, the communities around the lake all the people there's not that many people who live around the lake, but those who do live there year round, they rely on the lake ice for transportation. So it's like you can only get there by boat during the summer, and then you've got this couple months of bad ice when you're just cut off. And then once that ice is nice and thick, they're driving trucks across it. Yeah, yeah. No, they do some ice. Yeah. Oh yeah, yeah, yeah. No, they're strong people. They're really strong people. Yeah. Somebody met me. We had only known each other's papers, like our research. And then my Siberian colleague, she met me in person the first time, and she saw like I'm, you know, I don't know, people on Zoom can't tell, but I'm like relatively small, right? I'm strong and hardy, right? But she said, "Oh, I thought you would be much bigger and stronger," because she knew that I worked on ice, right? So, okay, I'm glad you liked my papers. Yeah, yep, yep. Yeah, Stephen. So I personally have not cut through 6 feet of ice, so I'll just own that. But chainsaws, so usually we'll tackle with chainsaws and then move in with ice saw and start to use like ice tongs to pull out the big chunks. Yeah, it's an endeavor. Yep, yep. Sorry, there was a question back here. Yep. Sure. Yeah. Microplastics in Baikal and other lakes. So yeah, at Baikal, we had just seen the study that was done on Lake Havsgol in Mongolia, which is a super remote lake, and it was showing high plastics. And so we assembled some sampling methods, and we did find microplastics in Baikal too, which is, I mean, it was just incredible to me because it's a huge lake and very, very few areas of the shoreline where people actually interact with the lake. So there are microplastics there as well. And I think at this point, microplastics are just everywhere that we look for them. And certainly the microorganisms interact with them. They eat them, and the effects of them are largely still unknown. Yeah, and there are other people in this audience who know a little more about microplastics too, if you wanted to say anything more. I know it's a real topic of concern here. Yep.
But you're looking at climate change effects on ice coverage, duration, that, and what happens to the ecosystem. Long-time research on Lake Tahoe, back to the observation,
Yeah.
Yeah. It is a winter ecosystem. Yeah. Does that help inform research on what might happen to ecosystems and yep. Climate change?
Yeah. Yeah. So thinking about what we can learn between ice-covered systems and systems like Lake Tahoe that have a winter that doesn't freeze, but where the mixing is extremely important. And I would say that our international network is very conscious of that opportunity to start to anticipate what we're going to see in the winters when lakes that have historically frozen stop freezing, and we'll start to, and luckily there are a lot of people working on the modeling of that, you know, doing these computer simulations of what happens in these scenarios. And I know that Alex, I don't know where he went to, but he's done some of this modeling in ice covered systems as well. So it's of intense interest, I would say, to study these systems as sort of analogs of where these ice covered systems are going to be tomorrow, right? Yeah. Yep.
Washington, education, knowledge, and how the human action with the environment and
yeah.
Talk about anything, how you see data of that.
Yeah. Yeah. So question is about how scientists interacting with communities and sort of, you know, learning from each other. And I would say that is one of the things that really drew me to this position, because there is a lot of partnership that already exists here between TERC, the other research institutions in the area that are working here, and then also, you know, the managers, the policymakers, the nonprofits who are working on conservation and restoration here. So I'm coming into, you know, a real ecosystem of organizations and individuals who actually already care. And so, you know, in most other places where I've worked, you know, there's still a job in kind of making people care, or, you know, and then there's a job in making the connections to the people who are doing the management and the policy and the nonprofits, And, you know, here we already have a long history and a lot of strong relationships. And so it is a huge attraction to me. And I know, you know, one of my bosses is in the audience tonight, Vice Chancellor for Research. And I know that that I feel comfortable saying that UC Davis is really very committed to increased engagement in engaging communities in our research and education. Yeah, yeah, for sure. Yep. I think we had one over here for a little while. Yep. Do I have an angle that I'm going to build on Charles and Jeff's work? Yeah, I mean, this is another attraction of the job. I mean, when I saw this job ad, I was just like, oh my gosh, this is an amazing opportunity because, you know, not only the things that I just mentioned about the engagement here, but also that there's been such a strong foundation of ecology and also physical sciences here with the engagement of both scientists and engineers. And so I feel like, you know, I have this opportunity now coming in as an ecologist where I can really work together in collaboration with a good understanding of the ecology and also the physical dynamics and a lot of continuing excitement and commitment from the scientists and engineers to try to put those worlds together. Yeah, I think it's, I'm really, really excited about that. Yep. Yep. Charles. Thank you.
So excited about you. I call Tahoe connection. Some of the people here may not remember the 20 years when we had the Tahoe back.
Yes. Yeah. Yep.
Which had a dual purpose. We were actually transporting research on the environment, in other words, ecology and conservation together. In Russia, which almost it didn't exist at the time. This went on for 20 years. Dr. Slaughter was the last director of that.
Yep.
And people began to lose interest in connection. Threat of war seemed less. But, I think this is wonderful that they're bringing these back together and if political realities. Maybe we join the Tahoe interconnection. So important for here.
Yeah. 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 So for the Zoom folks, Dr. Goldman was reminding us of the wonderful legacy of the Baikal, the Tahoe Baikal Institute or the Baikal Tahoe Institute. Tahoe Baikal. Tahoe first. The Tahoe first. Yeah.
Dave, previous concerned about war.
Yep.
Here, breeze, so did the funding. I went.
Yep.
Rise again.
Yeah.
And
Yeah.
the other thing that I wanted to mention, Lake Baikal, the highway from north to south.
Yeah.
For big trucks.
Yes.
So it really was the ice road.
Yep. Yep.
Quite important.
Yeah, yeah. Lake Baikal is a ice road north to south in Siberia. I mean, really critically important connection during the winter. Yeah, yep. Let's see. Okay, I think. Oh. I know. I'm looking over a lot of our field team is here. So I think they just, do you guys want to say anything about recent paraphyton field work? Mike?
Yeah, right now we're seeing So at the end of the season, when it starts to, warm up, it sloughs off. You can see it all out. That was really summer. Here's been doing great. So frequently adults are
Want to report it? Citizen Science Talk.org. Us, our actual album research is bigger than ours. So you would be contributing to our research.
I'm going to summarize this for Zoom. So citizensciencetahoe.org is where you would report if you see some blooms of algae near shore, the periphyton. And our Director of Field Operations, Mike, was telling us about the cycle of algae that they've been observing out there. So, okay. Other questions?
Yeah, it's definitely interesting things that certain areas. This big.
So, and so for folks on Zoom, we're talking about the pattern of algae growth and how varied it is around the shoreline. Yes.
So how are the places spent in Lake Tahoe affected by winter? Know of ways to increase the summer population?
So I do not know very much about the mysids in Lake Tahoe yet. And actually, I have not yet worked in a lake that had mysis. So I don't know that much about how they're affected by winter. So apologies for that. It is week 7 for me. I'm learning as fast as I can, but I do appreciate your question. Okay. All right. Well, I just appreciate so much all of you showing up and really look forward to meeting you all and talking more in the future. Thank you.